Hello students, now we'll be studying about paramagnetism, or you can say the paramagnetic material. Earlier we have seen about diamagnetic material. Okay, so what was happening in diamagnetic material was the net magnetic dipole moment in an atom was getting equal to 0 because each electrons were cancelling out the effect of each other. But here it is not the case. Here what happens in paramagnetic substance, the net magnetic moment of all the electrons in an atom do not add up to 0. So there is net atomic dipole moment in a paramagnetic substance, which means that suppose this is a material, it will have some paramagnetic, it will have some magnetic dipole moment. They all will be in random direction. Everyone will be in random direction, but each atom will have some net atomic dipole moment. Whereas in diamagnetic material, what was there? There was no net atomic dipole or magnetic dipole moment in a single atom. So here what happens? There are many magnetic dipoles, like number of atomic dipoles which make up to this material. But what happens? They are randomly arranged. They are randomly aligned. So what happens when you cut out a small unit area? When you cut out a small unit area, then the net magnetic moment is equals to 0 because they are not aligned in any direction. Okay, so unless and until they don't get any external force, they will act as net magnetic moment is 0. Though each and every atom has a magnetic moment. Okay, make it very clear. In diamagnetic material, it was that each and every atom does not have magnetic moment because the electrons cancel out their effect. But here there is magnetic dipole with each and every electron, but they are arranged in a random manner. Okay, so the net magnetic moment will be equal to 0. So here I have written, but in absence of external field, the net magnetic dipole of any volume is still 0 as the dipoles are randomly arranged. Okay. An example for this type of material is O2. So on applying external electric field, what will happen? On application of external electric field, suppose I am applying external electric field, what will happen inside it? The atoms or the magnetic dipoles inside it will try to align itself in a single direction, that is in the direction of magnetic moment or the external magnetic. Though they will not be exactly in the aligned manner, it will not be 100%. That's why I have drawn this cross arrows. Okay, but it will try to align itself. It will try to align itself in the direction of external magnetic field. I hope this is very clear to you. It tries to align itself. Okay, why? Due to the magnetic torque. Whenever there is a magnetic dipole in a magnetic field, it experiences a torque. We have already derived the theory about it. So this will experience a torque. Suppose it was in a random manner. It was in this manner. What happens? Due to external magnetic field, the torque applies on it and tries to get in the direction of magnetic field. It tries to get in the direction of magnetic field. So what happens here? It tries to align itself in the direction of external magnetic field that is provided on it. Hence what will happen? It means that it is weakly attracted. Unless and until there was no external magnetic field, they were not aligned and net magnetic moment was also 0. Which means that when some external magnetic field is applied to it, it tries to align and it gets attracted. It gets attracted because it is in the same direction of the magnetic field. But it is very weakly attracted. Okay. So here I have written, hence they are weakly attracted by the external magnetic field. So this was all about what is the origin of paramagnetism. Now we will be talking about the properties of this paramagnetism. Now first property is that there are atomic dipoles in paramagnetic substance, which means here it is shown that there are atomic dipoles in paramagnetic substance. The atomic dipole is not equal to 0, which it was in the diamagnetic substance. Okay, so here there are atomic dipoles. Second is they are weakly attracted to the external magnetic field. Here you can see they are aligned, so they are weakly attracted towards the external field. अगर external field है, ठीक है, वो क्या करता है? उसके पास खुद की मैग्नेटिज्म नहीं है, but it has magnetic dipoles. So क्या करता है? अगर कोई external force आया, yes, if there is a force, I'll go in your direction. So it is weakly attracted towards it. Okay. Third one is magnetic susceptibility is positive and small. Why it is positive? We know the formula M is equals to zeta H. Okay. Now H is the external magnetic field, M is the internal magnetic field. Both are aligned in the same direction. That's why zeta is positive. And the value of zeta is very small. It is also in the range of 2.3 into 10 raised to minus 5, sorry. And that is for aluminum, and for oxygen it is 10 raised to minus 6, which means that once again here also the zeta is very small, which again shows that it is very weakly attracted. Suppose here if you apply external field of 10 raised to 5, then here you will get about 1 Tesla. 10 raised to 5 Tesla magnetic field is applied externally, then internal magnetic field will be around 1 Tesla. I hope you are getting it. Next, the relative permeability is slightly greater than 1. You can once again look at from over here. Mu r, that is relative permeability, that is 1 plus zeta. Here zeta is positive but very small. Positive but very small. Which means that relative permeability will be greater than 1 as zeta is positive, and it is 1, so it will be slightly greater than 1. It will be very small and slightly greater than 1. Okay. Now here in non-uniform magnetic field, they move from weaker to stronger region. So what does this paramagnetic try to do? Whenever it is and it enters in an external magnetic field, it tries to move from weaker section to stronger section. Like the example I had given in the previous lecture about the students. Suppose I am a student, I want to study something but I am not getting it exactly. मेरे दिमाग में कुछ जाता नहीं, but I want to study. तो क्या करूँगा? Whenever I get a chance, I enter a room. I will try to go near the stronger students or the strong students who are intelligent, so that I can study from them. तो मैं क्या करूँगा? Weaker region से निकल जाऊँगा. I'll try to move towards the stronger region. Okay. And the next is magnetic field lines become more dense. Okay, I'll show you over here. Magnetic field line becomes more dense inside the material. Suppose this is a material. This is the external magnetic field. So what will happen? It will try to connect all the magnetic field that is going around it. It will try to attract the magnetic field. So here you can see, here the density is less, whereas here the density has increased, which means that the field lines inside the material are very dense. Okay. And the last thing is here the seventh property. Experimentally it is observed that magnetization of paramagnetic material is inversely proportional to absolute temperature. Okay. I forgot to tell you one thing. Why are these randomly aligned? Why these atoms are randomly aligned? Because they have some energy due to temperature. Due to temperature they have some energy. So electron will move zoom, zoom, zoom in all the directions. Okay. So it will have net magnetic moment that is random. So if you try to decrease the temperature, if you decrease the temperature, what will happen? The kinetic energy that the electrons are having will decrease, which means that atom will start aligning in a single direction. Atom will start aligning in single direction. So there will be no random motion. So it depends on temperature. On decreasing the temperature, it will align itself. Dipoles will align. Okay, there are two reasons for dipoles to align. One is decrease in temperature and second is on application of external magnetic field. If you increase the external magnetic field, what will happen? It will try to align itself more and more. If you increase the external magnetic field, if there is a small magnetic field, few will align, few will not. If you increase the magnetic field, it will force all the magnetic dipoles to align in single direction. So there are two reasons. One is decrease in temperature and one is increase in magnetic field. Okay. So here it is saying that magnetic moment is inversely proportional to temperature. So here M is equals to C B0 upon T, where B0 is the external magnetic field, T is the temperature and C is Curie's constant. So here I can I'll write this. We all know that M equals to zeta H. Also B0 equals to mu 0 H. Okay. So can I write this? I can put this value in this formula. So it will be zeta H equals to C mu 0 H upon T. So from here H will get cancelled, which means that zeta is equals to C mu 0 upon T. This is known as Curie's Curie's formula. And this is Curie's constant. Curie's constant. This is known as your Curie's constant. This is for paramagnetic material only. Okay. I hope this much portion is very clear to you. Yes, one last thing. If you go on decreasing the temperature, there will be a point when all the magnetic dipoles have already aligned itself in one direction. All the magnetic dipoles have arranged itself in one direction. If you go on decreasing the temperature, as you go on decreasing the temperature, the magnetic dipole will start aligning itself. But there will be a point where all the magnetic dipoles are arranged in a single manner or aligned in single direction. So after that, if you still go on decreasing the temperature, there will be no effect. Which means that after saturation point, that point is known as saturation point. So after saturation point, this law is invalid. This law becomes invalid. Okay. So अगर एक बार align हो गया तो और temperature कम करने से कोई फर्क ही नहीं पड़ता. It is already aligned. You cannot align more than that. Okay. So after a certain temperature, it does not align itself, or the temperature does not affect the magnetic dipole of that substance. Okay students, I hope this topic is very clear to you. So keep studying. Thank you. Have a nice day.